Hello and welcome to 37th lecture of video course on tribology. Topic of present lecture is a friction and lubrication of gears. It is the second lecture in this series. In previous lecture also we have same topic, lubrication, friction and lubrication of gears. We mentioned in previous lecture that there are two sources of friction when we discuss about the gears, and those sources will decide what will be the efficiency. So, we say that if we do this kind of analysis, we will be able to figure out what will be the efficiency, and that lubrication part is going to decide what will be the durability of the gears, what will be the survivability of the gears, whether the gears are going to wear out or not. And if they are going to wear out, what will be the rate of wear? That depends on lubrication, kind of lubrication mechanism we are using. And we discuss about the rolling and sliding. We said that the pitch circle diameter, particularly in spur gears, there will be rolling motion. And in rolling, mostly there will be elastro-hydrodynamic lubrication mechanism, because the pressure generated at the rolling contact is very high, is substantially high, maybe say more than 1 gigapascal. And when the pressure is more than gigapascal, naturally there will be thickening of grease or liquid lubricant, whichever we are using. That thickening will convert semi-solid to the almost solid and liquid to the semi-solids. In addition, there will be elastic deformation. That is why we say the elastro-hydrodynamic lubrication mechanism. In addition, there will be sliding. When we talk about the pitch circle diameter, there will be rolling, but below pitch circle diameter and above pitch circle diameter, there will be some sort of relative sliding, relative velocity of the interface that will be causing some sliding or friction at the surface. So, we need to control that sliding using lubricants. Then we discuss something about the solid lubricants. So, we can use a solid lubricant something like a nylon. We can use a solid lubricant like polymers. We can make a gears directly from the polymers, then we do not require extra lubrication, but depends whether we have application of light duty, medium duty or heavy duty. Medium duty load application and heavy duty load application, we will not be able to utilize polymers in those situations. So, polymeric materials are suitable only for the light duty applications. For heavy duty, we need to use some sort of liquid or semi-solid lubricants. Solid lubricant coating can be done, but it will wash out and we need to replenish one way or another way. We discuss about major factor in as a tooth toothing power loss. We say that toothing power loss can be divided in two subcategories. One is called ideal power loss, that means there is no load applied on the gears, but still there is a speed variation or a speed change that will cause a churning effect. You can see this kind of the tooth profile, and we assume this whole tooth profile is submerged in liquid. What will happen? There will be some sort of churning effect, some sort of splashing action when this wheel start rotating, and that splashing is going to consume power. That will not be without power. So, that is the ideal power loss, and this ideal power loss will be higher when speed is higher. Another word, churning loss, windage loss will be higher with increase in speed. It will heavily depend on the speed. Other one is load power loss. We say that this kind of power loss will be depending on how much load we are applying. More and more load, more and more power loss. So, to simulate this, what we use a relation something like this, the P load is equal to Fr into Vg. This is the sliding velocity. This requires a sliding velocity. With the rolling velocity, we are not considering there is a power loss, and this is a force which is being applied at the contact surface, or is a friction force, and that can be represented as a coefficient of friction into normal force on the surface. So, P load, which is required of the power due to the power loss due to the load, will be given as a P load equal to mu, the coefficient of friction, normal load at the interface into sliding velocity. We know sliding velocity will be 0 at the pitch circle diameter. So, the power loss will be 0. Other thing is that whether this mu is remain constant or not, Wn will remain constant or not, Vg will remain constant or not. In actual case, mu is a highly variable, will change with the radius of curvature. It will be depending on the geometry, it will be depending on the normal load, and Vg is a sliding velocity. That sliding velocity itself will change continuously. It will be maximum at the extreme of gear tooth, will be 0 at the pitch circle. So, this depending on what is the interface or what is a contact point, the sliding velocity will be decided, or in other words, this power loss due to load is highly variable, is continuously changing with position to position. It will not be a constant value. So, we need to take some sort of mean value. Now, we talk in the mean value, naturally we need to find out the mean value of the coefficient of friction also. That mean value of coefficient of friction often is represented in a number of variables. That is a normal load. If the load is very high, there is a possibility of converting from full film lubrication to the lustro-hydrogen lubrication to the mixed lubrication and to the bonded lubrication. And we know very well coefficient of friction will be different in all 4 regimes, or in other words, gear may experience all 4 regimes. That will be dependent on the speed as well as normal load which has been applied to the gear interface. Now, when we are talking the gear load, naturally the phase width also matter, because stresses which are generated, plastic deformation or elastic deformation that are generated will depend on the phase width also. In addition, there will be rolling velocity. We say the pitch, V pitch is a rolling velocity. Rolling velocity of pinion, rolling velocity of gear, or summation of this rolling velocity is going to affect the mu value. Then comes the viscosity, eta. So, this viscosity, higher the viscosity, there is a more possibility of higher the value of mu m. But this mu m will depend on the range. There is a possibility that we take a very thin oil, almost negligible viscosity, but that is going to cause gear to operate in bonded lubrication. In that case, mu m will be higher. So, overall we need to see the package, we need to see the what is the factor, how it is depending. This is there is no direct relation between mu and eta, but there will be indirect relation depending on the load regime. Then comes surface roughness of the gear and pinion surfaces. That is why we are writing here the R composite is the surface roughness composite surface roughness. Now, when we discuss about normal load in a previous lecture, we mentioned that there is a contact ratio. We discussed about the contact ratio. Say if the contact ratio is more than 1, that means some time of the rotation 2 gear teeth pair are coming into contact, and because of that there will be change in the load. Quite possible during the engagement load slowly increases, reaches to a steady value, and after the time of the disengagement again this load start decreasing. So, one gear tooth is going to experience this kind of load variation. So, we need to use that kind of the load when we try to find out what will be the coefficient of friction. And another thing, there is a possibility of change in the coefficient of friction itself, because when you are talking about the so the few degree rotation of the gear wheel, we are able to see the coefficient of friction itself is going to change. It may vary a little bit, depend on surface roughness, depend on the other geometries, depend on the material pair, but it will reach to the 0 value at the pitch circle diameter. The mid value, that is why this is 0, Before that there is a higher value and after that there will be a higher value. But a pitch circle diameter, this coefficient of friction is going to be 0. That is why we need to model it properly. It should come with this kind of characteristics. Maybe initially there is some sort of undulation, there is some sort of variation, maybe statistical thing, but it will come to 0 at the pitch circle diameter when we are talking about spur gear, helical gear. Of course, when we talk about the hypoid gear, again in those situations this velocity, this coefficient of friction will not be 0, there will be sliding and that will cause some sort of some value of coefficient of friction. So, we discussed about normal load in our previous slide. Now, we are going to discuss about the rolling velocity, the V pitch. Now, P this is a summation of the rolling velocity of gear and pinion, and it has been observed with higher rolling velocity coefficient of friction will decrease. With higher velocity coefficient of friction is going to decrease. What is the reason for that? You see, if I am assuming these are the gear wheels, maybe I can assume this is a pinion, this is a gear and they are rotating. What will happen? There will be some sort of tangential velocity generated at this interface, and this having some sort of profile, so it will get some sort of liquid over here, and with a rotation dragging action on the liquid will happen, and more dragging action will happen when there is a more higher and higher velocity. Obviously, then this is a more like a pumping action. This oil, this liquid lubricant is going to get pumped from this side to other side, right, and that is going to generate more and more lubrication. We say that if initially there was a boundary lubrication or dry lubrication, because of this pumping action, liquid will be at the interface and then it will be Lastro-Hardon lubrication or full flame lubrication or mixed lubrication, entirely depending on the load, how much load we are applying. And this is why that we are showing this kind of curve as a coefficient of friction as a VE, which is a summation of rolling velocity of gear 1, rolling velocity of gear 2 is increasing, coefficient of friction is going to decrease. Of course, there will be a final limiting value, it will not continuously be increasing. And often this coefficient of friction is represented in terms of VE, we are using this relation. Now, we say that mu is proportional to VE power minus 0.45, that is the inverse relation. You say that this is advantageous. This figure shows higher and higher VE will be better and better results for us, better and better efficiency. But this is what we are talking about the load. When we discuss about the load, there is a load dependent friction, there is other friction also, what is known as a spin losses, churning losses. That happens because of the spin velocity of the gear, and they have this kind of profile. Naturally, dragging action will be there, and higher dragging action will generate higher friction losses or high spin losses. And many times high speed gear spin losses are far more or far greater than load dependent friction losses. But slow speed, larger size gear, this gear this load dependent coefficient of friction is generally higher compared to the spin losses. Then we discuss about we are discussing about arc composite surface roughness profile, and we say this composite surface roughness can be given as a RQ1 square plus RQ2 square and square root of this whole this summation. RQ1 is the surface roughness of maybe say pinion, so RQ2 is the surface roughness of gear. We need to use this for calculating arc composite, or we say arc composite can be given as a square root of RQ1 square plus RQ2 square. Now, it has been observed that when we manufacture the gears and start operating those gears, they have a different surface roughness compared to what we get after certain duration, and that what we use a word running in time. This is shown over here, the milling operation, hobbing operation, grinding, lapping, honing. So, these milling and hobbing are generally gear manufacturing processes, grinding, lapping, honing or the super finishing operation to remove the asperities from the surface. And what we are able to observe here, the surface roughness is a 2.3 to 4.6 micron. So, it is very high surface roughness and it cannot be used as it is. That means, after milling we require some sort of super finish operation. However, if you are using this milling operation and maybe say for low speed operation gears, we are using this after running in maybe say couple of hours or 100 of hours, whichever the running in time for the gears, what we get a lesser surface roughness as almost half of the surface roughness. So, what we use finally when mathematical simulation time, we need to use a running in surface roughness. We cannot use start surface roughness because that is not going to give reliable results, and we cannot really operate also. When the surface roughness is high, we cannot operate gears at the higher speed. We need to operate at the lower speed, remove all the debris, whatever the worn out from the surfaces, and change the oil and then come to this so that we can do analysis. So, surface roughness has importance. We say we need to take care of surface roughness after running in duration. And for detail, you can refer to this book, W.J. Bart's The Lubrication of Gearing, as a complete book on lubrication of the gearing, and we say that this topic. Now, what we talk about the gear surface roughness is highly related to the film thickness. When we are trying to decide which kind of lubricant regime is going to work in that case. So, this is a equation, elastro-hydrodynamic lubrication equation. H min is a minimum separation between the gear pair, which generally happens in some micron level, and this is radius of curvature or the interface. It gives in the load parameter, velocity parameter, material parameter, and load parameter, which we have earlier discussed when we were discussing about the EHL, elastro-hydrodynamic lubrication mechanism. This depends on the load, depends on the phase width. Here is the slight changes there. When we were discussing earlier, we used to we were using the symbol F for the force. In case of the gears, we are using symbol F for the phase width. We say that depth of the gear, width of the gear. E prime is effective Young's modulus, R prime is effective radius. We assume that there are two surfaces and both are having some radius of curvature. So, we need to find out effective radius of curvature. When coming to the velocity parameter, we say that it is depending on the viscosity. It depending on the velocities, summation of velocities. Again, it is also depending on the E prime and R prime. Finally, the material parameter, it depends on pressure viscosity coefficient and E prime effective Young's modulus. So, we need to account these factors. Now, what is the sensitivity? What we are able to see, they are slender. They have been simulated when they drive this kind of relation, and of course, I can say that when we refer different books, different literature, everywhere this relation is slightly different. Maybe if somewhere you will find this in 0.073 or multiplication factor will be 2.65. This velocity will be in the power 0.67. So, there will be delta variation depending on the experiments performed, and this is the curve fit equation. We are not solving partial differential equation to get this kind of relation. It is more like curve fit equations, and wherever the results are matching, they give coefficients according to those experiments, and so there will be always slight variation from one experiment to other experiments. And what I have observed, overall results are not going to be drastically changed. There will be delta variation, but that is within permissible limit. So, once we know these factors, we can find out what will be the film thickness. Now, once we know the film thickness, we can find out a specific film thickness, which is going to decide whether the gear is under boundary lubrication, mixed lubrication, or elastro-hydrodynamic lubrication. I am leaving the possibility of full film lubrication, because gears will not operate full from lubrication. At most they can be operated in elastohydromal lubrication, but we have this kind of a division. We say that when the lambda is lesser than boundary lesser than 1, we need to say that this is the boundary lubrication. There will be more and more respiratories in contact, maybe having some productive layer, lubrication layer of order of a nanometer to the micron, maybe say lesser than micron. 1, 2, 3 is a mixed lubrication where the boundary lubrication is also existing, and to some extent full film lubrication is also existing. And this lambda greater than 3, we are saying the full film lubrication, but it is the elastohydromal lubrication plus film lubrication. We can say the elastohydromal lubrication can be treated as a full film lubrication because there is no contact. Generally, on the rolling surface, a near pitch circle diameter, this kind of surface is possible when there is a high pressure and is deforming the surface, and there is a lesser surface roughness. So, this regime depends on both. First is the H min, there is a minimum film thickness, a minimum separation, and depends on the surface roughness profile. And what we have seen in previous slides, that if manufacturing process is not very good, what we are going to get high surface roughness, and surface roughness may be the 3 micron or 2.3 micron or 3 microns even after running in time. If 2.3 micron and this is also 2.3 micron, that means we need to keep a film thickness more than 5 micron between the gears, and if the film thickness is more than 5 micron, there is a possibility of lesser positive drive, and that will also again in those situations we will be losing the efficiency from the gear. So, we want to operate gears as close as possible, but we want to avoid the wear also. It is more like a trade off. We want efficiency, positive drive, we also want no wear, and that is why we need to have some sort of trade off. And it has been observed that as this lambda is which is the capital lambda is increasing, okay, when it is reaching to the 1, there is a sudden change in the relative life. If I compare when the lambda is 1.5 and with the lambda 1, we find there is a substantial change. Or in other word, under boundary lubrication cases, generally gear is not going to give us very good life, reliable life, and that is the reason why we use the lubricant additives in gear oil. Whichever oil you choose, we need to use some sort of EP additives, anti-wear additives in those gears. If you are not able to use those additives, naturally performance will be worse, it will be towards the boundary lubrication, and gear life will be much lesser, relative gear life will be much lesser. But if there is a jump from 1 to 1.5, we are able to see there is a jump, substantial jump, significant jump in relative life. So, that is important for us to find out what is the surface roughness, find out what is the film thickness. You can see here film thickness itself is depending on number of parameters. If we increase the viscosity, film thickness is going to increase. If we decrease the load, film thickness is going to increase, but sensitivity is different. Well, here the sensitivity is roughly 0.7, while here the sensitivity is of 0.13. So, there is a significant difference of 5 times different in power itself. So, we need to see whether what is the more suitable, increase in speed or increase in decrease in the load, whichever is more beneficial, we should go ahead with that. But again the trade off will come whenever we are increasing the velocity. Naturally, there will be more churning losses. When there is more churning losses, there is a power loss. So, we need to have some trade off in that. And whatever we have discussed in this, these are the fixed values. So, in this case, we are using the viscosity, we are using the value of alpha, they are constant temperature values, and we know alpha may not be that high temperature sensitive, but viscosity will remain high temperature sensitive, and sensitivity of viscosity is very high compared to alpha. As the temperature increases, this eta is going to change, and that can be given by a number of relations, can be predicted. We took discussed over 2 common literature two common relations. One is a Walther's relation, other is Vogel's relation. We know the Vogel's relation requires 3 constants, while the Walther's relation, which is given over here, requires only 2 constants. Again, when we see the Walther's equation from a different book, sometimes we get this constant as a 0.6, 0.7 and 0.8, but we know very well whenever we are discussing of the gear oil, this viscosity, kinematic viscosity represented as Sandy-Stokes will be in numbers, maybe say 30, 40, 50, 60, 70, 80, 90. So, when we are talking about the 80 plus 0.8, it is not going to make much difference when you are talking the log and log scale. Of course, this is on log and log scale. Once we know the viscosity of the two different temperatures is a 40 and 100 degree centigrade, we can find out the value of A and value of B, and once we find this kind of relation can be used iteratively to find out what will be operating viscosity. Question comes, how to iterate this? We do not know the temperature, we are not discuss anything about the temperature. We are saying mu depends on regime, regime depends on the film thickness and surface roughness. Now, film thickness depends on viscosity, viscosity is depending on the temperature. So, number of equations need to be solved together. It is a highly complex. Even good computer program will take maybe say 5 to 6 hours minimum to give one result. So, that is why many times what we say that we will use some sort of physical modeling or understanding based modeling. We know what is happening, we try to do modeling on that. So, these are the couple of diagrams over here. We say that when we try to do modeling, we know there will be 0 velocity here. The coefficient of friction turn out to be 0 over here. There is almost 0 sliding, but here there is a more sliding. We say gear tooth can be divided at the pitch level, above pitch, below pitch, this flank and face. Generally, the flank will be having higher wear rate compared to the faces. That is why we say that this portion is more subjected to pitting, is more subject to the failure compared to this portion, and we need to keep very good thickness of the gear over here. Similarly, when we talk about the sliding, here the sliding is much wider compared to here, and that is going to give the friction surface, and this is what we say is more critical to analyze, and here importance comes from the role of the lubricant, or the lubricant gets its importance over here. If we use lubricant, first thing, even in rolling action, it is going to separate, it is going to generate elastohydrodynamic lubrication mechanism, it is going to separate two surfaces. So, lubricant is important over here. In addition, when there is a sliding, naturally lubrication is important. Sliding is going to generate higher friction, and to reduce that friction we require lubricant. But problem is that liquid lubricant itself gets sheared, so it will give some sort of coefficient of some friction. But when I compare solid to solid sliding friction with a liquid solid sliding friction, we find substantial change. That is why we prefer liquid shearing compared to the solid shearing, right. And here it is also mentioned, whatever you do, as we are not going ahead with full film lubrication and even elastohydrodynamic lubrication, it happens only near to this surface, this circle. That is why there will be some wear, and that wear can be given by sliding velocity, can be given by load, normal load, given by the material and the hardness, material constant and hardness, right. So, it is heavily dependent, and now we choose a bad material having lesser stiffness, naturally the wear out will be more. If we apply more load, wear out will be more. If we apply more sliding, wear out will be more. So, many times what we say that we can compare this as stuffed teeth, standard teeth and high contact ratio gears. We say that when this profile, now we say that this profile is extending beyond certain limit, that is going to give a high contact ratio, but along with the high contact ratio is going to give very high sliding. High contact ratio is required from force point of view. Higher the ratio, lesser will be the force. Obviously, that lesser will be stresses, but had the contact ratio, there will be more sliding, more friction. So, again when we do the friction analysis, we find there will be change, and if there is a wear of the gear, even though we keep a high contact ratio initially, it is going to decrease with the time. It is not going to be constant. This contact ratio depends on the time duration. If there is a more wear, surfaces are getting damaged, then contact ratio will be decreased. So, in other words, we say that gear will never have infinite life. It will have only finite life, depends whether it is a 20,000 hours, 30,000 hours, 40,000 hours. If you require more and more life, you need to reduce the wear volume, even though whatever you do the good design initially, but when talk about the topology, we need to reduce this wear rate. Wear rate can be reduced if we are able to reduce the sliding velocity, we are able to increase the hardness, we are able to reduce the load. So, one way or another way we need to do or reduce this K1. We know very well K1 is heavily depend on the liquid lubricant. More and more lubrication, this K1 should be decreased, but larger and larger K1 will larger and larger liquid lubricant is going to produce more and more churning losses. So, again the trade off is required. Higher friction may lead high temperature, that may lead more volume of the wear. So, this is a combination, and that is why we required some sort of procedure. We say determine effective value of velocity, that is a per circle diameter you find out omega, and then you find out the value over there. Then you find if you are able to calculate load, the normal load, then effective modulus of elasticity and effective curvature, effective radius. So, that is a first step. We need start. We need to we generally have a data available to us. Velocity can be determined based on the module, number of teeth, and that is which is going to give the diameter and omega. And then load can be figured out or can be calculated if we know the power transmission or we know the torque applied on the gear. That is going to give us the results of the load. Then modulus velocity or effective modulus velocity, that we call two material property, which is the Poisson ratio and Young's modulus, and that is going to give us the effective modulus of elasticity. Then comes the curvature. Here we are talking the curvature. This curvature is different. This is the curvature. We are not talking about the piscicle radius. We are talking of the convex shape of the gear, and that curvature is important. We need to find out either using piscicle diameter and pressure angle. You know the piscicle, the curvature radius can be calculated using piscicle radius and sine of the phi or sine of the pressure angle. The multiple, that product is going to give us curvature. Then next one is to determine and estimate the effective temperature. We are not introduced any temperature relation. We need to balance, or we say go for the thermal balance, thermal equilibrium, to find out what will be the effective temperature. Then once we know the temperature, we should determine the viscosity. As we know, viscosity is going to get affected with the temperature. Higher the temperature, lesser will be viscosity. And if possible, calculate pressure viscosity coefficient as a function of temperature. This also may reduce. Then calculate the film thickness. Once we know the film thickness, compare it with the roughness and decide what will be regime. Once we know the regime, we can find out what will be the coefficient of friction. So, coefficient of friction may be on if it is a mixed lubrication, it may turn out to be lesser than 0.1. If it is a bonded lubrication, it will turn out to be between 0.1 to 0.3. So, it depends on the regime and a number of parameters, we can decide what will be the coefficient of friction. Again, we have given a big expression or big dependence, but those are indirectly depending on the coefficient of friction or indirectly affecting the coefficient of friction. What we say that we require so many calculations, that is a one way, but we can go ahead with other way, which is that we can find out the effective temperature or maximum temperature or flash temperature at the gear interface using this relation. We say what is this relation? We say that this relation is been derived from a rate of heat generation. How to give the rate of heat generation? There is a mu which we are trying to figure out. This is a sigma d, that is stresses which are causing the deformation, and this is the relative velocity. At any time, what will be the velocity of the pinion, velocity of the gear, and then what will take a difference. Naturally, this velocity will be 0, or this difference in velocity will be 0 at the pitch circle. That is why we are not saying that this Tf will come at any time at the pitch circle. It will be away from the pitch circle. The coefficient of friction is also will be different. At the pitch circle, it will be 0. Now, coming to the sigma d, which is the compressive stresses generated in a gear profile. You can see there is a convex shape, and we can find out the radius of curvature of this surface. Once we know that this radius of curvature, we can find out what will be the effective radius of curvature, that is Ri. Similarly, if we know the material of this surface, material of gear and pinion, then we can find out Young's modulus, which requires the Poisson ratio of the gear material 1 and gear material 2. Once we have Young's modulus, effective Young's modulus, we have effective radius of curvatures, we can go ahead with finding what will be the sigma t, because we know sigma t is a strong function of material properties and radius of curvature, which have been discussed in our basic module, when we discuss about the elastic deformation. Now, this is a sigma d, and we say there will be a parabolic distribution. Pressure will be maximum in the center and lesser at the away, and this continuous variation will happen. Every point will have a maximum pressure, and maybe say after 0.1 degree, 0.2 degree, it will have a lesser pressure. What we are once we know, we calculate a sigma d and substitute in this, what we are going to get this equation in terms of normal load and face width. Larger the face width, lesser will be the maximum temperature or flash temperature. And in addition, what has been mentioned over here is a B1 and beta 1 and beta 2. That beta 1 and beta 2 can be defined as a coefficient of thermal contact. Coefficient of thermal contact for the surface 1. Coefficient of thermal contact for surface 2, that is a beta 1 and beta 2. And what is this thermal constant? Thermal contact coefficient, you say that it depends on the conductivity. If I know the thermal conductivity of the material, that is going to give can be represented as the lambda, as a small lambda, and we know it need to have some sort of dissipation, and a specific heat which can be represent a specific heat into density, that is a C as a specific heat and rho as a density. This is going to give as a beta value. Larger the beta value, lesser will be the temperature. We say that if material conductivities are high, it can dissipate the heat faster and faster. Then naturally there will not be accumulation of the temperature, and there is no accumulation of the temperature. Naturally, thermal equilibrium will be faster, and we will get a lesser temperature, overall lesser temperature. So, this maximum temperature is depending on velocity or relative velocity. Larger the relative velocity, larger will be temperature, and then it is also depending on the sigma t, which is given in a function of load, phase width, Young's modulus and radius of curvature. And this W, small w, is this patch contact length, which in our earlier relation and earlier lectures, what we represented this as a B or 2B, 2 into B. This was contact patch length was represented. If you refer an earlier lecture, you will get a similar expression what we are doing here. That is elastic effective radius of curvature, effective Young's modulus. When you substitute, we are going to get the same relation. So, after substituting all, what we are getting, this is some multiplication factor into coefficient of friction, if we are able to find with the boundary lubrication, mixed lubrication, EHL, and based on that coefficient of friction, we can find out what will be the temperature. Naturally, if the coefficient of friction is a 0.1, and if I compare with the 0.05, coefficient, this temperature will be reduced to half. Reduction of the temperature in half is significant. Actually, we should point out there should be more and more lubricant additives to at least maintain bonded lubrication, and there should be some carrier fluid which can carry these boundary additives and try to keep some separation, that will give a lesser coefficient of friction. Then comes the relative velocity, and this is a given in the expression, the beta 1 into V1, beta 2 into V2. Now, think of extreme cases. Naturally, when we are talking about the relative velocity, they will have a negative velocity as well as a positive velocity. But we are going to talk about extreme cases. Assume that V2 is not there, V2 is 0. When V2 is 0, what we are going to get a maximum value of this V1 will turn out to be overall, if I compare V from 0 to some positive value, this will give me maximum value. A maximum value of V1 minus V2 will turn out to be V1 if V2 is positive. But if that is the situation, this is a V, and here also this will turn out to be 0. This will be square root of beta 1 into V, and this overall expression can be modified if we want to find out the extreme cases, the tip conditions. That is going to turn out to be something like this. In this case, V1 divided by beta, we know beta 1, beta 2 has been replaced, and we know V1 can be represented as omega into radius. That radius at any contact point, we are not talking about the pitch circle radius, at a contact point, that can be given in terms of number of teeth module, that can be given in those terms, because we know that for the different gears are generally standardized. When the gears are standardized, naturally they will have some module, some gear number of teeth, and based on those, this number R can be figured out, can be calculated. So, overall expression will turn out to be this omega is rotational speed divided by beta, load divided by phase width. Do not get confusion. Many times we have given F as a force, but here we are giving F as a phase width. It is in mm, it is not in Newton, while W is in Newton. Now, here m is a module, Z is a number of teeth, and we are talking about this E prime as the effective Young's modulus. So, if you want to keep a low value of TF, what is required? We require a lesser speed, a larger beta, larger phase width, lesser load, lesser module. It is a very good thing, the lesser module in this case, a lesser number of teeth, and lesser effective Young's modulus. While we know that increasing number of teeth is going to reduce the load. So, they are having some sort of dependence. When this dependence comes, whatever the final relation comes, we need to take that as that into account. Now, here Fz is depending on the number of teeth, and so the couple of numbers are shown or in this table. We say when Z is 17, this value is 0.813. So, here the number of teeth, increasing number of teeth is going to decrease the Fz value. That is why I say, and this is a proportionality. Here we are increasing number of teeth, that is going to increase the temperature. Increasing Z is going to increase the TF value, but increasing Z is going to decrease Fz. So, this is more beneficial compared to this. It is only having power 1 to 4 or 0.25, while this case power is 1. So, we need to compare it, and wherever the benefit comes, we need to take a decision based on that. What will be the number of teeth can be decided also based on the temperature calculation. We can find out the beta with thermal properties of the material. We can find out omega from the rotational speed, whatever is being given, and if we can find out the temperature individually for the gear and individually for pinion. Generally, it will be more for the pinion, so we should go ahead with the pinion surface in this case. And that this coefficient of friction will depend heavily surface roughness as well as the film thickness. Film thickness itself will depend on number of material pairs. So, we need to as a gear design, when we talk about the gear design, it will not be simple like this, it will be based on combinations of number of teeth, the Young's modulus, effective curvature, load, speed parameters. So, there is no one way rule that we need to have only these parameters. It is always a trade off, it is always a combination, its overall package gives a lower coefficient of friction, a higher coefficient of friction, and we know if the temperature is higher, viscosity is going to decrease, and viscosity decrease is going to decrease the load carrying capacity. So, it is basically iterative scheme, it is iterative scheme. That is why we try to utilize a lot in this this kind of analytical expression or curve fit expressions. If we are requiring detailed calculation, it will take many iterations. So, if we are designing initial level gears, we should always recommend this kind of curve fit equation, find out the TF, find out the viscosity, again find out what will be the load carrying capacity, what will be the H minimum, because H minimum itself is going to depend on the viscosity, and when that is depending on viscosity, H minimum is going to affect the mu, and mu is going to affect the TF. So, there is always a perfect combination. Obviously, we are going to get some temperature which is heavily dependent on itself. Its temperature is depending on itself in one way or another way. So, this is what we say about pressure dependent coefficient of friction. We can calculate churning effect, which is generally about the high, if viscosity is high, churning effect will be higher side, and that will be required whenever there is a speed of operation is very high, but generally we say the gears are recommended, generally gears are recommended as a speed reduction device. They are used to reduce the speed and increase the torque. When increase the torque, so in those particular application, I feel that the load dependent power loss is more dominant compared to speed dependent module. Speed dependent churning effect may turn out to be lesser than 50% when we talk about the real application of gears. Generally, we do not use a gears for the high speed application, but if it is required, then we should calculate the churning effects. Otherwise, using only the pressure load dependent friction losses will be sufficient for us. So, we will see how to calculate, we will just take one example to find out what's how to utilize these relations. So, that we know the coefficient of friction in the different regimes. If it is coefficient of friction in a dry case, and I mentioned about one of the example that polymers can be used as a gear material. When we use a polymer as a gear material, we should check what is the validity of those gear materials. That is why we are taking possibility of scuffing of the high temperature. When the temperature is very high, there is a possibility of plastic deformation, plastic flow, and the two materials will get welded, and that is known as scuffing. Scuffing is one of the failure. We generally do testing of scuffing on various gear machines, but if there is a proper design of the gear, proper design of the lubrication mechanism, there will be very low probability of scuffing, but it is possible when we use some sort of polymer gear material. We need to find out, is there any possibility of scuffing. So, example says compare scuffing possibilities of nylon versus nylon and steel gear pair. Here again, here we are using two nylon gears, where here we are using one steel gear and one nylon gear. We are not talking about the steel, but we are talking about nylon and steel. And when you compare the coefficient of friction, what we find, nylon on nylon coefficient of friction is slightly more than nylon on the steel, slightly more. So, we can start with the dry lubrications. We say there is no liquid lubrication, and the mu can be taken as it is. It's a dry lubrication mechanism. So, we can implement that and try to find out, maybe we require some data for calculation. So, for time being, we are taking the pinion gear teeth as a 17, module as a 3 mm, that is going to give us a 51 mm pitch circle diameter. And if we want the radius, we can divide by 2, that will be the pitch circle radius. The face width, in this case what I have written in the B is F, is a 30 mm, and omega is a 150 radian per second, while power which has been transmitted from this nylon gears is slightly lower side, is 850 watts. So, based on the power we can find out, based on the power and omega and pitch cycle radius, we can find out what will be the Wn. Of course, as we are assuming that the pressure angle will be 20 degree. Without pressure angle, otherwise it will be very difficult for us to get the results. Then this is the phase width, and this is by mistake it is written the B here, it is a B F. So, this B is 30 mm or B is F and F is 30 mm. The module has been defined, number of teeth are defined, and we can find our Young's modulus, effective Young's modulus based on the material pair. We know the nylon material pair, we know the other pair is a nylon and steel, and Young's modulus of both the materials are known to us, Poisson ratios are known to us. We can substitute those values, can find out, and this table is going to give showing the results. When we talk about the nylon effective Young's modulus is roughly 2000 megapascal. We say 2 gigapascal. While when we talk about the nylon versus steel, we are getting is roughly the 4 gigapascal. Otherwise, Young's modulus for the steel is very high, is almost a 200 plus gigapascal. But when talking about the pair, naturally lower value will be dominating. That is going to decide what will be the final value, and that is showing the 4 gigapascal. So, once we know E prime, we know Z here, we know M here, we know F, we can find out W. We this omega has been given to us, and coefficient of friction from previous table we can figure out the 0.2, nearby 0.2, even though we know that nylon and steel will give slightly lesser coefficient of friction compared to nylon versus nylon, but we can take same value, almost same value is a 0.2 to find out what is the relation or what is the overall temperature. Is there any possibility of a scuffing? Is there a possibility of high temperature, high flush temperature? So, once we use these parameters, of course, there is a beta parameter which can be figured out for the material combination, and here we are able to see that beta for nylon versus nylon is roughly 0.417 10 to 6, while in case of nylon versus steel, because of thermal conductivity, because of high thermal conductivity of steel, this is a substantially high value. Compare 0.147 with a 180 is almost 360 or is the 360 times, very high value, high comparison, and that is in a denominator. So, higher value of beta will be preferred to keep temperature lower side, and that is what is going to happen. You can see here. For nylon versus nylon, the temperature is 161, very high temperature for the nylon to bear it without flow. Of course, in a number of with a number of fillers it can be increased, the temperature can be increased, but still we cannot say there will be elastic deformation, there will be perfect elastic deformation. They are when temperature is this high, naturally contact will be subjected to slightly plastic deformation. It will not be only the elastic deformation. While coming to the steel versus nylon, this temperature is only 19.5 degree, very low value compared to 161. It is not only the 1/8 of that or just 12.5% of that, but with increase in the temperature, sensitivity changes drastically. So, this combination will be preferred. We say that whenever we choose a gears, maybe one polymer gear, but other solid material gear which has a very good hardness, which can which has also the high thermal conductivity. If the gear has a hardness and thermal conductivity, surely we can use this kind of pair, one solid material pair, one solid material gear or pinion, and other as a steel or some material which has a high thermal conductivity. That will be preferable compared to this kind of thing. But we know very well for the number of application in home appliance is the nylon gears are used. Key reason being that their duty is lower side, they do not transmit power continuously, and it is generally recommended. We talk about the mixture. When we talk about the mixture and we operate the mixture, we say we do not operate more than 10 minutes, because we will continuously operate for 10 minutes, the temperature will continuously increase, and we may find that gear versus gear is going to get engaged, or there will be cold weight, it cannot be separated, cannot be rotated after that. And that is the reason we want to keep operation for some time, not beyond certain level, because there will be thermal instability, there will be more flow and there will be cold welding. And this is an important aspect. Whenever we choose a gear material, we need to think about good thermal conductivity, because we know the contact point there will be high temperature, there is a possibility of high temperature, and there is a metal to metal contact. And in this whole example, we took a coefficient of friction equal to 0.2, but if we provide some sort of lesser coefficient of friction, then it is going to affect the results. If I decrease this coefficient of friction, maybe say 10 times, naturally this temperature is going to reduce to 10 times. But in those situations, this nylon, selecting nylon will not be having any use. It can be removed, or we can choose some alternative material. So, we will continue our gear topic in our next lecture. Next lecture, we will be considering what kind of the failure analysis we can do, or what are the possibilities of the gear failure. We have explored the possibility of gear failure. In this case, is particularly scuffing failure, which happens at the high temperature, the lack of lubricant, or very high coefficient, because of the high coefficient of friction and lesser thermal conductivity. But there are other possibilities of failure of gear we will be exploring in our next lecture. Thank you.